In this video, we're going to take off from where we were at before in terms of significant figures. If you recall, in our last segment, we went through the first few of these in here and talked about how many significant figures each one of these had. For example, we said that 6 had 3 significant figures. This 5 here, this 5, and this 0 were all significant. In this segment, we're going to tackle numbers 7 through 13 and talk about why some of them you do apply significant figures and where some you do not. And then how do you do that if you do not apply the significant figures? So first one is number 7. If we look at number 7, we know it's written in scientific notation. So scientific notation is a way for scientists to write very big numbers or very small numbers condensedly in a package that's more useful to us. Now the beauty of scientific notation is it doesn't really change any of our significant figure rules. We still follow the same rules we see over here. The beauty is almost all scientific notation that we're going to see is going to be rule 2 because we're going to have some decimals in there. So following the same rules, we see a decimal, we start on the left-hand side, and we work our way over. With scientific notation, it's always going to be whatever non-zero is up here in front of that decimal. That's going to start our measurement, and then everything over to the right is. The beauty of scientific notation is you always have significant figures or measured values in your numbers in scientific notation. There's never a reason to write a 0 that isn't measured here. I sometimes tell students, if you're not sure if a 0 is significant or not, write it in scientific notation, and if it falls off, it wasn't significant. So for example, here, this 0 wasn't required, but we put it there to show significance, so it is part of the measurement. So number 7 would have 3 significant figures to it. Now, if we move down to number 8, we have 33 people. And at first you're like, okay, that's easy, 2 sig figs. But if you think about it closer, we're not really measuring here, we're counting. So when you have a counted value, like we have 33 people here, counted values do not apply to the same significant figure rules. Okay? So that goes down to rule number 4 over here, that any number that is not measured has an infinite number of significant figures. So since 33 people is not really measured, it's only counted, we can't really have a possibility of 33.1 people. This is a counted value, so we would say it has an infinite number of significant figures. Along the same token, if you look at number 9, the pi, the number pi is a mathematical representation of circles. So it's not a measured value, it's actually a mathematical number. As a result, since it's not measured, it again would fall under category 4, being an infinite number of significant figures. Now looking at number 10, you look at that number and say, okay, 43, 2 sig figs. But if you look at it closely, you'll notice there's no label here. So with no label, that number to us really does not indicate measured. All of these numbers have a label on them telling us that they've been measured values. However, 43 does not. So that 43 could be an exact number. It might be a measured number that someone didn't put the label on. It could be lots of things. But since we don't know what it is and we don't know that it's measured for sure, we get to assume it's rule number 4, infinite number of significant figures. So again, we'd have infinite for number 10. Now number 11, you look, it actually has an equal sign in it. So we're saying we have 100 centimeters equaling 1 meter. First thought again might be, oh, meters and centimeters, these are measured. But if you think about it, we really aren't measuring anything here. We're just saying that if I have a meter, by definition or by mathematical rule, that's 100 centimeters. So these values aren't really measured. The reason why I put this one in is because we'll use a lot of conversion factors in chemistry. And if you see these conversion factors as measured values, you're always going to be reducing your significant figures down to 1, and that's not what we want. So your conversion factors that are exact, like this one, are not measured, so they have an infinite number of significant figures. Now, number 12, we have 4.5 million geese migrating each year. Now, again, is this like number 8 where we're counting? Or is it more like number 5 where we have a big number that gets measured? So at first look, you might say, well, it's 4.5 million geese, so you're actually counting the geese. But can we really count 4.5 million geese during migration? It's really not possible. So the way we actually determine migration patterns isn't through counting, it's through measuring. So what we'll do is we'll go to a lake and we'll measure or we'll count small groups, and then we'll extrapolate from that, what would it be in bigger areas and across the whole sky and different times of the year. So this number is really a measurement that comes from these individual sets of geese. So it's kind of like a counted value that comes from measurement. So in this case, like number 12, it is considered a measured value. So because it is a measurement and you don't actually individually count each goose, this is measured. So we would say it has 2 sig figs. So this would be 2. And then last but not least is money. When you deal with money, as long as money isn't like number 12 where you're estimating like net value from a person and you actually are counting like dollars and cents, it's a counted value. So money would have 3 sig figs, would have an infinite number of significant figures, just like 33 people would or pi would. Now with money, it's really easy to round it because money we always round to the nearest cent. So it's kind of an easy one to say, well, just round money to the nearest cent and you're good for that one. Okay guys, that's some of the kind of more challenging ones that we run into in terms of dealing with significant figures. Combine that with the first 6 of our more normal measurements, and that really should give you a good picture of what is a significant figure and what is not a significant figure. All right. Now in our next segment, we're going to take this idea of counting the significant figures and apply it to what happens when we start doing math with these numbers. All right, thank you.